we're going to look here at volumes using cross sections. This is something that commonly gets called the disk method or the washer method in Calc 1. There is another method for doing volumes called the shell method, which is a good one, but we are not going to be covering that in here. So I'll post some notes up for you on that shell method in case you are interested, but you're not going to necessarily have to use that on the final. You don't have to get tested on that. So we're going to do volumes with these disks and washers. All right. So first, we're going to take things back to geometry here and look at something called Cavalieri's principle. So what this involves is the volume of two different objects. So in the picture here, we have two different stacks of pennies, and one of them, the pennies are stacked up in a nice straight cylinder right here. All right. And then the other one is kind of a bent cylinder type of shape right here. The pennies have been kind of pushed off center a little bit. Okay, but what we're going to say about those two stacks of pennies, and you can kind of see the details over here in the right-hand picture, is that both stacks are made up of the same amount of pennies. So the heights of both those cylinders are the same, the straight cylinder and the bent cylinder. Okay. And then what this kind of shaded yellow plane in the middle here is trying to show is it's showing that each of these stacks is made up of the same type of object. They're both pennies in cross section. So each cross section is the same size. So one penny there is the same size as one penny over here. Okay. They're not like different sized coins. Yeah, so Felipe's put it a nice way in the chat there. The height and radius are the same in both stacks. Yeah, very nice. So if I asked you about the volume of these two stacks of pennies, and said like, okay, which one has a greater volume? The one on the left, the one on the right, or neither? What do you think? Which of these has the greatest volume? Left, right, or they're the same? Let's see. You can stick an answer in the chat there. So we've got a vote for the right-hand cylinder, the kind of bent, wonky cylinder there. Another vote for the right one, because it looks a little bigger, maybe, how it kind of bulges out to the side like that. Let's see if anyone else would like to vote here. So we've got a vote for the same, another vote for the same. We're tied between right and same. No one's voting for the left one. All right. And now we've got 3 votes for same. So Patrick came in with the tiebreaker there. And yeah, you guys who were voting that they are actually the same volume, you are correct. So it's kind of a weird mind trip type of situation here. Because yeah, sometimes we'll look at these two stacks and say, oh yeah, the one on the right looks larger because it's wider. The pennies have stuck off further to the side there. But these two stacks actually have the same volume. And that's what Cavalieri's principle tells us. If two objects have the same height, which that's what this picture on the right shows us, height is the same, and the same cross-sectional area Okay, so that's what this picture is showing with those yellow dashed circles right here. Same cross-sectional area. It's a pennies area in both cases there. So if we have the same height and the same cross-sectional area, then the volume of both those objects is the same. Interesting, right? It's kind of a funky geometric principle there. The volume of both objects is the same. Okay, so here what we're looking at, we're saying that there's the same number of pennies in both stacks. So same number of pennies because the stacks are the same height and it's made out of, you know, a uniform number of pennies. So the same number of pennies makes those two stacks. So same number of pennies means that we're going to have the same volume in both stacks. So kind of another way to think about this is that, you know, the volume of one penny is the same as the volume of another penny, you know, within a degree of measurement there. I mean, they might be off by like a tiny little decimal place or something if one penny is maybe older and people have rubbed it down a little more or something like that. But generally we can consider that overall one penny is the same size as another penny. So if you think of a single little penny's volume, we're taking, I don't know, let's estimate here. There's probably about 15 pennies in this stack, something like that, 15 to 20 pennies. So we're taking the volume of that single little penny, and then we're adding up more and more of those little individual slices of volume. We come up with the total volume for this cylinder, but then we've actually added up the exact same number of little slices of volume over here. Okay, same number of pennies. So whatever the volume of 15 pennies is, we have that much volume in both stacks. It's just one has been stacked up straight and the other one's been stacked up in a kind of curvy way. So yeah, that's the idea that we're going to use here for doing our volumes with cross sections. So we can find the volume of a solid by adding up the individual little volumes of a lot of cross-sectional slices. Okay, so yeah, like how we're doing here with the pennies, if you think of the volume of one individual penny, that would be like a little cross-sectional slice of this object. And then to find the total volume of that object, you could add up however many slices, however many pennies there are in the full stack. All right. So yeah, that's the principle we're going to use there. Okay, so questions so far, just kind of looking at the pennies there, the whole geometric principle we're using. Oh yeah, Felipe, good point there. Also multiply by how many pennies there are. We could certainly use that in this example there, like the volume of one penny times 15 to get the full stack, something like that. Yeah. All right. Well, yeah, we're gonna do this and notice how we're gonna add up the volumes of a lot of these things. So hint, hint, when we add up a whole lot of things, that kind of starts to sound like a summation or a Riemann sum. We're going to make an infinite number of these little cross-sectional slices, and this whole thing is going to turn into an integral. So surprise, that's where we're going.